I'm going to talk about the alpha-beta pruning for the Minimax algorithm for game trees. Now, if you don't know what I'm talking about, please take a look at my videos on adversarial search and the Minimax algorithm. For now, alpha-beta pruning. So if you looked at the videos for Minimax, you know that triangles up is the maximizer or player max, and the triangles pointing down is the player min or the minimizer. The goal of the maximizer is to obtain the highest possible score in the game. The goal of the minimizer is to minimize the score that A gets, right? So have A get the lowest possible score, hopefully so low that actually this player wins as opposed to the first player. Well, the trees look like this, right? And now the Minimax algorithm looks like this. The minimizer, so all the triangles pointing down, are going to look for the minimum possible value, the value that gives the least amount of points to A. In this case, B will look at the minimum of 3, 12, and 8, right? So it's going to look at the minimum value of these, 3, 12, and 8. Then C is also a minimizer. It's one of the other options that the minimizer does. And it's going to look at the minimum values of these nodes. And when the minimizer is faced with the option of playing on D, it's going to look for the minimum of these values. Once each subtree gets the minimum, the maximizer, this guy, right, is going to look for the maximum of the values for B, C, and D for that level. So here's the thing. Let's look at what that looks like. So the minimax from the root, from A, is going to look as the maximum of the three minimums, right? The first branch, the second branch, and the third branch. So let's look at the first branch. The minimum of the first branch, that is 3, 12, and 8, the minimum here is 3. Let's look at the last branch. The minimum of 14, 5, and 2 is 2. Now let's look at the middle branch. The middle branch is going to look at the minimum of 2 and then some other 2 values. But here's the kicker. Here's the kicker. So the first value that it sees is a 2. Now, a minimum of 2 and any other 2 numbers is going to be either 2 or a number that's smaller than 2, right? However, after this gets resolved, okay, let's call this Z, this term Z. After Z gets resolved, I'm going to get a value of 2 or smaller than 2. But then I have to take the maximum, and there's already a value that's bigger than that, 3. 3 is bigger than 2, right? So why bother computing the values of all these other nodes or perhaps subtrees, right? If I already know by looking at the first node, I already know that this guy is not going to be selected. This is never going to be the maximum of the 3 numbers, right? Because 3 already is. So the question then becomes, well, if I'm not going to explore this because I already know it has no use, so once C looks and it sees that it has a node of 2, then it doesn't need to explore the other 2 subtrees, okay? And that is the key here, because if you don't explore these subtrees, you save a lot of time. Well, that's the intuition. So we can save time that we spend exploring nodes and computing values if we know that they're going to be of no use. So what's the intuition here? Well, the biggest intuition is the following. If I already have a value of, in this case, 3, right? And then here, I know that the value is not going to be bigger than the maximum value so far, than the best value for A, actually, is not going to be bigger than that, then why bother, right? In here, in node D, I will see 14 first, so I don't know if it's, that still can be a better value, right? That's not going to be a very good value, but, you know, maybe the minimum here is bigger than 3, right? So I still have to explore this until I get to 2, and then I know that the minimum is 2. So let's see how this works intuitively in a kind of algorithm, right? So this algorithm is called alpha-beta pruning, and it's going to be a depth-first search, just like Minimax. We're going to keep track of 3 parameters. Alpha which is going to be the best value for max, for the maximizer. So it's the highest possible value the maximizer can get from the root node down. And beta is going to be the highest possible, the smallest possible value that the min can get from the root node. Basically, alpha is the best value for player max, and beta is the best value for player min. Now, each node that we explore is going to keep track of its alpha and beta values. And also, because each node has to have a definitive value, we're going to keep track of that value. Okay, we're going to denote these in the example that comes after this as a list of alpha in red, beta in blue, and the actual value of the node in black. Now, at each step, as the algorithm explores the trees, at each step, if the player or if the node that is exploring is min, I will ask whether the value that I have is worse for max, because min wants to get things really bad for max. So I'm going to ask whether the value of the node is less than alpha. If that's the case, then I'll take it. I'll take any value that's worse for max, right? Now, if it's not worse for max, I will keep exploring to see if there's a value that's going to be worse for max. If none of them is worse for max, I will just, return the best subtree, and I will be updating beta with that worst value for max, or the best candidates as worst value for max. Now, if the node is max, if max is exploring a node, then it's going to try to find values that are worse for min. Basically, the value of the nodes, it's going to compare the value of the nodes against beta. And if the values are bigger than beta, that means that it's worse for min, right? And it'll take it. If it's not, it'll keep exploring and it will return the subtree that is best for max at that point, but not necessarily worse for min. It's going to return an alpha that's the minimum between the value that it has and the alpha that it's exploring. Let's see an example. So let's see we have the same tree that we had before. Here's my little vector of alpha, beta, and the value, initial values. Now, because I'm going to be finding minimum and maximum, right, I need to find a maximum for alpha. So I start with the smallest possible value in your language, whatever that is, right? Because I need to find minima for beta, I will start with the highest possible value. And because this is a maximizer and I want maximum values, I'm going to start with a value of negative infinity, which is the minimum possible value. So anything that I find from this point on is going to update these values. That's the key intuition. So what happens is depth first search, right? So I'm going to explore node B. And in B, I'm going to explore this number 3. So it's depth first. When I get to B, I will pass a vector with this alpha, this beta, this alpha, this beta, and a value initialized for beta, for B. B is a minimizer, a min node. Min nodes want small values, so therefore I initialize the value to the biggest possible number, so any number can be smaller than that. And then what I ask is, I will first check whether 3 beats the value that the maximizer has as its best. I will ask, is 3 less than alpha? Is 3 worse for the maximizer? That's what I'm asking. Is 3 less than alpha? Well, alpha right now is initialized to negative infinity, so 3 is not less than alpha. So then what I'm going to do is I'm going to say, well, beta is going to be the minimum between 3 and whatever beta is so far, okay, which is infinity. So I'll update beta. And so far I have negative alpha, 3, and 3 is the candidate for the value for beta so far. Then I'm going to explore the next node under B, which is this 12, right here, 12. And I'm going to ask the same thing. Is 12 less than alpha? Do I beat the maximizer? Well, 12 is not less than negative infinity, so I don't beat the maximizer. Well, do I beat the current best value for the minimizer? Beta, I'm going to update the beta, the best possible value for the minimizer, with a minimum between 3, whatever it was before, and 12, the node that I'm exploring. That means beta stays at 3. And then I go to explore the next node, this one 8 here. I'll ask the same questions. Does 8 beat the maximizer? Is 8 less than alpha? No, it's not. 8 is not less than infinity. Well, then beta is going to be the minimum between the existing beta value 3 and 8, right? Well, the minimum is still 3, so 3 stays, and I return the value 3 because that was the best beta, and it's the same as the best value for beta, for B. This is depth first search, so now we go back. A will now query B, and the value for B is going to be 3, right? So I'll say now the maximizer wants to see if 3 beats the value that it has for beta, and it doesn't. 3 does not beat the value that it has for beta. The value is initialized to 3, right? Because it's the maximum value so far. And then I ask, is 3 better for me than what the minimizer has? No. So then I will say, well, alpha is going to be the maximum of alpha so far, which is negative infinity, and the number 3, which is the number 3. 3 is bigger than negative infinity. So I'll update that. Then I'm going to explore node C, and C is going to explore this node over here, which is value 2. I will pass to C, I will pass the same alpha, the same beta, and then positive infinity for the default value. Okay, so I will ask the same questions. Is 2 less than 3? Is 2 worse, right, than the best value for the maximizer? And it is. So I will take it. I don't need to explore anything else. 2 is worse than 3. That's all I need to know for the maximizer. It's better for the minimizer. I don't need to know anything else. I will just update that value. I don't need to explore any more nodes because there's no point. Okay? 2 is worse than the best value for the maximizer, so I won't explore it. And then I go up, right? Because it's depth first search. So I'll go up and I will ask, is 2 greater than beta? Infinity. Now, remember, when it's a max node, I will compare against beta and I will make sure whether the number is greater or equal than beta. And it's not. So then I will say, well, alpha is going to be the maximum between 3 and 2, this value that I just passed, and the maximum is still 3. So what I'm saying here is that for the maximizer, the value 2 didn't do anything because the maximum value is still better than 2. So then I go to explore D, and D is going to explore its first node. Again, I pass the alpha and beta from the previous node, from the parent node, and this infinity is just an initializer for D, right? Remember, minimizers are initialized with positive infinity, maximizer nodes are initialized with negative infinity. All right, so then I do the same comparison. Is 14 less than 3? Is 14 worse than the best choice for the maximizer so far? No, it's not. Well, then I update the value to 14 as well. As you can see here, the value is updated to 14. So then what I'm going to do is I'm going to say beta is going to be the minimum between infinity and 14. And the minimum there is 14. And then I'm going to explore it. See, I update beta, and then I'm going to explore the next node, 5. Is 5 less than 3? Basically, is 5 a worse choice for the maximizer? No, it is not. So then I will get the minimum. Beta is going to be the minimum of the regular beta and the value so far, which is 5. Okay? So I will update beta to 5. Then I'm going to explore the next node, 2. And I will ask the question, is 2 less than alpha or 3, right? And 2 is less than 3. So because 2 is worse than the best for the maximizer, I just return. I don't need to make any comparisons. And that's the 2. Now, I'm going to go back up here to A. And I'm going to ask, is 2 greater than beta? And it's not. 2 is not greater than infinity. And then I'm going to say, well, alpha is going to be the maximum between 3 and 2, which is still 3. I have no more nodes to explore, so I return this value and I assign it to alpha. So the maximizer, I'm sorry, to A. So node A now knows to travel to the node that has value 3, So it knows to travel this way, because when the minimizer moves, the minimizer is going to pick the worst possible option, which is this, right? So the maximizer already knows where to go. And the key thing here is that we pruned, we did not explore, in this case, two subtrees. Point of discussion, if we had reordered these elements here, and we have had the two at the beginning, we would also have pruned the other two branches. So this algorithm can result in high improvements. Now, if you want, you can pause now the video. Here's an algorithm that you can turn into whatever language you want of the Minimax, of the, of alpha beta pruning. Now, a few things about alpha beta pruning. Pruning does not affect the final outcome, so the Minimax algorithm will play the exact same moves. Sorting moves, like we saw in the last subtree, improves the alpha beta performance, and perfect ordering has a runtime of b to the m divided by 2, with b being the branching factor of the tree and m the levels. It's an exercise of meta reasoning, so reasoning about how we reason. This is what alpha beta pruning is. I hope this example has given you a good idea of how it works.